let's just talk briefly about the properties of alkanes. Some of this stuff should be review from general chemistry. The one thing that we can say about alkanes, they are very unreactive relative to other organic compounds, compounds with other functional groups. It's really for that reason that the word paraffin is used as another way of saying alkane. So, we've all heard of paraffin wax. All that is just a series of very long chain alkanes, usually 20 carbons to 30 carbons, and that's it. But paraffin itself is synonymous to alkane. It's just used in slightly different contexts, but it means the same thing. So paraffin, though, means it just has little affinity for other substances. That's what the word paraffin itself means. So there are, however, two reactions that alkanes will readily undergo. One that we're very familiar with, the other one probably not as much, but the combustion reaction is one that, whether or not we've studied it, we've definitely all seen it. Anytime you turn on a Bunsen burner, methane, CH4, reacts with the oxygen in the air, and if it's complete combustion, carbon from the organic compound will become CO2. The hydrogen from that organic compound becomes H2O. So carbon dioxide and water are produced, and if I were to balance this, I'd need 2 waters and then 2 oxygens. So obviously a very useful reaction in that a large amount of heat is given off. That's what powers our Bunsen burners. That's what, if you have a natural gas furnace or water heater, that's what powers them. The combustion reaction happens anytime anything burns. So when you're burning wood in your fireplace, you have the cellulose in the wood, which is an organic compound that undergoes a combustion reaction to make CO2 and H2O mostly, but there's also other things. There's also pure carbon, which is left behind and which is given off as the soot of it. There's also carbon monoxide, CO, given off anytime that there is not completely enough oxygen available to react, which is almost all of the time. It's very difficult to get a totally saturated oxygen atmosphere unless you were to specifically try for that to be the case. So one problem with the combustion of organic compounds is that, look at this one product, CO2, something that we've heard a lot about recently. Anytime we have the combustion of any kind of hydrocarbon, carbon dioxide is given off, and as we know, that collects up in the atmosphere and contributes to a greenhouse effect and to climate change. So people have become recently much more conscious about the hydrocarbons that are burned. So anytime coal is burned to make fuel, for instance, a large amount of carbon dioxide is given off. Anytime petroleum products or gasoline or anything like that is burned to make an engine work, carbon dioxide is given off. So something that we should definitely be aware of, and we'll be discussing more as we go through this course. So combustion, something that any alkane, really any organic compound itself, will readily undergo. As long as it has carbon in it, we'll be able to react it with oxygen. That carbon gets oxidized to make CO2. Another kind of interesting reaction, we'll cover this later on. We'll cover this in the alkyl halide chapter later on towards the end of this course. But a reaction called radical halogenation is where the hydrogens are replaced with halogens like chlorine. And chlorines are very efficient at doing this in the presence of strong ultraviolet light. So you may or may not remember from first semester general chemistry that the energy of any kind of electromagnetic radiation is proportional to the frequency of that wavelength, and it's related by h constant. So h nu, where nu is the frequency. So when we have ultraviolet light present as a reactant, or a catalyst, I guess, to get a reaction going, we usually put h nu on top of a reaction arrow like that. That just means it has to be irradiated. We put it in a chamber with an ultraviolet light source in it. And this is a chain reaction. So we can halogenate just once by replacing one of the hydrogens. We can do it again on that one and again and again. Ultimately, if we keep going with this reaction, we'll be able to replace all of the hydrogens, and we could produce carbon tetrachloride, for instance, out of this methane, out of this CH4 that was produced there initially. So that's a reaction that can happen. Chlorines can abstract hydrogens from any type of alkane, and we'll talk about that reaction later. It's actually sort of useful. Just a quick little beat on the properties of alkanes. They're predictable trends in boiling and melting points, just due to increase in dispersion forces. These alkanes are all nonpolar. There are no electronegative functional groups to make any kind of dipole moments. So the only differences in properties between alkanes will come from their size or their shape. So if we look just at the number of carbons going from 1, 2, 3, 4, 5, 6, 7, 8, boiling point for one carbon compound, look at this, for methane way down here, minus 175, 2 minus 100 or so. It's not until we get up to 5 carbons where the boiling point has gotten above room temperature, right? So these are all 1, 2, 3, 4, those are all gases. So methane, ethane, propane, and butane in their standard states are gases at room temperature. Once we get to 5 carbons, once we get to pentane, we have liquids. And it's not until we get up to, I don't know, around C20 or so where we start getting solids. That's where I was talking about paraffins. Paraffin wax are alkanes that are large enough such that they are solid at room temperature. Also, between isomers of the same formula, the amount of branching, the amount of surface area that alkane has will dramatically affect its boiling point. So if I have pentane, 2, 3, 4, 5, versus neopentane, the straight chain pentane itself will have a higher boiling point because there's more surface area, there's more room for interactions for those dispersion forces to collect up between the molecules. So N-pentane itself will have a much higher boiling point than something like neopentane. Well,